a strong field, for example, 1.5 Tesla. 2, you have gradient coils, which can create pulsed magnetic field gradients. This is actually how you create the spatial encoding. And 3, you have an RF coil. The RF coil is used both to excite the spin system and also to record the signal. Now, this signal is very weak, and because of that, the entire system, the entire room, sits in an RF cage. So you have a very pristine electromagnetic environment. The problem is that MRI is very slow. Each acquisition takes several minutes. So there's a high risk that the data acquisition gets corrupted by motion. And to give you an idea of what kind of problems this can cause, we're looking at the cross-section of a pineapple here as an experimental setup. The bottom image is the pineapple without motion, and on the top you can see what kind of issues arise. There is blurring, there can be these duplicate ghosts or signal loss. And if you now think about the patient who's alive, there's so much going on. Blood is flowing, the patient is breathing, maybe the patient is shuffling around. So there's a lot going on. And this problem is as old as MRI itself. People came up with many clever strategies to work around it. One of these strategies entails that you use an additional sensor to record the motion state and then correct for it. And for that, you can use ECG or cameras, all kinds of sensors. And we believe that the radar is an interesting option here. Why? Radar is contactless. Radar can go through the skin, unlike optical light, for example. You can change the operational parameters at runtime, and I think this is where the SDR concept comes in, and it's very fast. Now, just to give you a very rough idea of what this could look like, let's say we have a transmit and receive antennas on both sides of the body, and if we illuminate the body with RF power, now a lot of the incident power will be reflected at the air-skin interface, but some of it will penetrate through the skin, depending on frequency, get reflected, bounce around, and will eventually reach the receive antenna. And the important thing is that the scattering of the electromagnetic waves inside the body is modulated by motion. Now, what are we actually doing? I think many of you know that there are different types of radar systems you can implement. Now, to get the ball rolling, we picked something simple, continuous wave Doppler. And this is our setup. On the left-hand side, you see the magnet room. We have 2 radar antennas for transmit and receive, which are connected to the SDR. Now, this is kind of a DIY prototype system, which is independent from the MRI scanner. That means that we have to synchronize MRI and radar in time. And for this purpose, we capture the RF pulses of the MRI scanner on the second channel of the SDR. Here's a flow graph. Now, I know this is small print, but we're going to zoom in on some of these details. At the heart of the matter is the Doppler calculation. This is unmodulated CW Doppler. So we take the reflected wave, we multiply it with the complex conjugate of the forward wave, determine the angle in the complex plane, and that's our Doppler shift. At this point, I want to highlight a presentation by Isabella Lenz and colleagues 2 years ago at GRCon. So if you're curious about Doppler radar for physiological sensing, I highly recommend that. Here's our hardware. We use an ATIS SCR and a Siemens clinical MRI scanner. In the middle, you see the scaffold that we use to mount our antennas. And I guess you can appreciate that we are very close to the subject. That means we operate in the near field of the antennas. That has some implications when it comes to how you calculate the Doppler shift, things like that. The antennas had been designed in-house for a different project. They have ultra-wideband characteristics. They are efficient, approximately from 0.5 to 10 gigahertz. So we thought, this is an interesting antenna, let's reuse them for our radar system. And one thing we like to do in MRI research is using phantoms. A phantom is some kind of object that mimics certain parts of human physiology. the reason or the rationality is that it's a lot easier to work with a phantom. You can scan it for hours, you can iterate. These are things you couldn't do in a human volunteer. And here specifically, we have built a phantom that simulates internal body motion in order to develop and evaluate the radar system. This is basically 2 compartments. You have a water tank, and inside the tank is a pendulum that moves back and forth. It's driven by a stepper motor, which is controlled by an Arduino. Here are some first results. What we're doing here is that we put the phantom in the MRI scanner, and we're running a very fast MRI imaging technique. This runs at 11 frames per second. It's so fast because we only acquire a single slice, and we're doing some special tricks to make it fast. And you can see the pendulum moving back and forth. So the position of the pendulum serves as our ground truth to see what the radar is doing. So on the left side, you see the X position of the inner compartment, and on the right side, the Y position. And overlaid in orange is the Doppler signal. Now these curves, they don't match. That's because Doppler encodes velocity primarily, not position. But you can see that we can recover a motion signal from inside this phantom. If we jump to higher frequencies, there's still a signal, but it gets noisier. So you can already appreciate that the optimal parameters are kind of frequency dependent and might need tuning, optimization, depending on the application. Going one step further, now we are acquiring a 3D volume of 40 slices. And this is a continuous acquisition. So the MRI scanner is running nonstop while the phantom is moving, and we record the radar at the same time. And then what we do is we take the raw data out of the scanner, and after the fact, we sort every sample according to the motion state as it was determined by the radar. And we use this technique, it's called binning or sorting, to kind of assign motion states to the raw data. And if you compare the top and the bottom picture, you can appreciate that this technique helps to get rid of the motion artifacts in the image. Going one step further, a different approach would be to have the radar running. The radar determines the motion state, and then you have the SDR trigger the scanner. So the MRI data acquisition is only active during a predefined motion state. Once again, we're using our phantom to test this. On the top, you see an image that was acquired without any triggering, and on the bottom, you see the same conditions, but this time we feed trigger pulses from the SDR back to the scanner, which results in a much clearer picture. I'm gonna skip over this in the interest of time. In a nutshell, we put together 2 custom blocks that allow us to feed a motion signal to one of our SDR transmit channels. Then we demodulate this signal. So it's basically AM demodulation in hardware to feed a TTL pulse to the scanner. Switching gears now, looking at volunteers. We're looking at a single slice that goes through the right chest. So at the top of this video, you see the lungs. It's a stark area. And below, the big organ is the liver and other abdominal organs that move up and down as the volunteer is breathing. And on the right side of the slide, you see the movement of the diaphragm, or the movement of the liver. Liver is moving up and down, projected over time. In orange, we overlay the Doppler signal from our radar system. So when we ask the volunteer to take deep breaths, we see a good agreement at 1 gigahertz between the image-based ground truth and the radar. However, when the volunteer is breathing more shallowly, which is kind of natural, you see that noise becomes more dominant. If we then jack up the carrier frequency to 4 gigahertz, once again, we have a very clean signal, even during shallow respiration. And I mean, one interesting thing is that, the so-called noise at 1 gigahertz, we think maybe this is motion from inside the body, maybe the heartbeat, some organs moving back and forth. So one of our aims is to decipher what we're capturing here. Now, as a radiologist, I want to know, can this be useful to actually, help us make better pictures? Here we are acquiring a 3D volume of the liver. Once again, we are doing continuous data acquisition on the MRI side and sort all these MRI samples after the fact based on the radar signal. On the left side is a reconstruction that doesn't use the motion information. On the right side is a motion resolved reconstruction. And if you look at the small vessels in the liver, or if you look at the diaphragm, the contour of the diaphragm, the lower panel, you just see a general boost in image sharpness. What's next? To be honest, we're just getting started. CW Doppler is a very simple technique, so we're excited to tap into more advanced radar schemes, see what's out there in the in the OOT world. Hopefully contribute some of our own custom blocks for medical imaging in the future. Frequency hopping is a topic, more antennas, always interesting. And one thing that we're excited about is to combine the strategy of using real-time, very fast MRI imaging with radar to kind of learn a patient-specific motion model, which can then be used for motion correction. Thank you for your attention.